Okay, engineers, let's start with the last subject. In this subject, what we are going to see is systems of differential equations. So, in this case, in summary, it will be matrix differential equation. Just like in your linear algebra course, where you have several variables and several equations, but now those equations have derivatives. And how are we going to solve it? Okay, this is just the introduction to that kind of differential equations and the solution, not to the method to solve it. Alright, now let's start with this example, this little example. What you happen to have here is two equations and two variables. So in this case, the solution is going to be x as a function of t, because it's x, derivative of x respect to the time. And then you also have the y as a function of the time, which is the solution for this. What happens here is that these two variables have relationship, meaning that the derivative of x respect to the time depends on different variables from the same variable x, but also from y. And the value of the derivative of y depends on x and y as well. So they have some relationship. So we have a system of differential equations. Okay. So check this out. For this example, what you have is two variables, and then you have two equations. So it is a square. The number of variables need the number of equations. Just like in linear algebra, you have the number of equations equal to the number of variables. Now for this equation, what you have is the derivative of x respect to the time depends on three different variables, x, y, and zeta. The same for the derivative of y respect to the time and the derivative of zeta respect to the time. So what we have to find is, here is x as a function of time, y as a function of time, and zeta as a function of time. Now check, you have three variables, and then you have three equations. So that is the rule. Okay? And let's use, and why this is a matrix differential equations is because we can write this system of differential equations in this way. Let's do some definitions. Let's do x vector equal to the vector of x and y, the vector of variables. Here in this course we are going to use the vectors in vertical form. Okay, now the derivative of x vector respect to the time is going to be derivative of x respect to the time and derivative of y respect to the time. So that's the derivative of the x vector. Now, the A matrix, this is going to be A matrix, is a definition, is going to be the coefficients of these variables, of these equations. So it's going to be 1, 3, 5, and 3. So the A matrix is the coefficients of this. Now, check this out. What happens if you have A matrix times x vector? So what you have is 1, 3, 5, and 3 times x vector. So check this. This is the A matrix and this is the x vector. And in the normal operations of the matrix, what you do is this row times this column. So what you have is x plus 3, 1, and then this row times this column, what you have is 5x plus 3y, and that happens equal to, this is a vector because the multiplication of the vector, and this happens to be the same as x plus 3y and 5x plus 3y. So in the end, because this is x plus 3y, that should be equal to the derivative of x, then this is equal to the vector of the derivatives, derivative of x respect to the time and derivative of y respect to the time. Okay, now a vector to be equal to another vector, then the first element must be equal to the first element, and so on. So what you have here is actually this representation of the equations, but you can represent this in in matrix form. So in the end, engineers, that this system of equation or system of this system of equations can be written like this: derivative of x vector respect to the time equal to the A matrix times x vector. Now this is the matrix differential equation. Okay, it's not big deal, engineers. Actually, you can do the same with the other one. Let's say that in this case x vector is x, y, and zeta. As you can see here, three variables. The matrix A is going to be the coefficients 6, 1, 1, 8, 7, minus 1, 2, 9, and minus 1. So what happens if you do A matrix times x vector? 6, 1, 1, 8, 7, minus 1, 2, 9, minus 1 times x vector, x, y, and zeta. So what you have is the first row times the column. This row times the column is going to be 6x plus y plus zeta. And here we have generated the first equation. And the multiplication of this is going to generate a vector. Now what about this one? This times this is going to be 8x plus 7y minus zeta. And then you have the second equation. And then this is this row times this column, 2x plus 9y minus zeta. Alright? And then, because this is the three equations, this is equal to, each one of them is equal to the derivative of x, y, and zeta. So this is equal to the derivative of x respect to the time, derivative of y respect to the time, and derivative of zeta respect to the time. So in the end, engineers, what you have here is the derivative of x vector respect to the time equal to A matrix times x vector. And in the end, you get the same matrix differential equation. Now, why is important this type or writing the system in this way? Well, as you can see, here is two equations and here is three equations. But in the matrix form, it is actually the same. It's just that here x vector is two components and here x vector is three components. Alright? So we can have four equations for four variables, but that will be a very long problem. We are going to deal with only these two kind of equations. Okay, now, what about the solutions? Okay, this equation is actually, the derivative is first order differential equation, matrix differential equation. Okay, now, the solutions. Okay, because it is first order, in the first unit what we saw is that the number of derivatives is the number of solutions. Well, here the rule changes a little bit. Here the number of solutions is equal to the number of equations. Okay, so what does that mean? Here, because you have two equations, or the matrix is 2 by 2 here, 2 by 2, then here what you need to find, because it's 2 by 2 or number of equation is 2, then you will need to find x1 vector, the solution, and x2 vector, the solutions. Okay, and the general solution, just like before, is the linear combination of those solutions, c1 x1 vector plus c2 x vector. Now this is for the 2 by 2 equations, but for the 3 by 3, what you have here is three solutions. So again, it's not only the order of the differential equation. Now it is the order of the differential equation, but also the size of the equations. In this case is three equations, so actually you can see in the matrix A is 3 by 3, the matrix. Okay, so what you have to find is x1 vector, comma, x2 vector, and x3 vector. And the general solution is going to be c1x1 vector for c2x2 vector plus c3x3 vector. Okay? So as you can see here, for the 3x3, then you will need more. The problem is going to be a larger problem. In 2x2, it is a short equation. Now, is it possible to have the 1 by 1? Yes. The example of 1 by 1 will be like this. Derivative of x respect to the time equal to x or 3x. And here the matrix A happens to be just 3, which is 1 by 1. Alright? And then the x vector is equal to just x, because it is one single variable. You can see here this is only one solution, x1 solution. Okay, but we have already seen this in the first unit. What we are going to do right now is 2x2 and 3x3. Okay, units, this is just the introduction of this kind of differential equations. On the next video we are going to see how to solve, we are going to see the solution and how to solve a 2x2 problem. Okay, see you on the next video.